you have e to the pi I tau over 4 everywhere, just by math, the only thing that's going to survive are even powers of e to the pi I tau over 4. I'm sorry, eighth powers of e to the pi I tau over 4. It's going to only have powers of e to the 2 pi I tau everywhere. We know that already. And they are going to be integers, built out of products of these kinds of numbers. So let's write out how the Q expansion begins. We know a priori that the coefficients are going to have to be integers, so let's take a look at them. So let's take a look at the Q expansion of delta. We know it starts with a Q, and the next few terms, the next term is 24Q squared, then 252Q cubed, minus 1472Q to the 4, plus 4830Q to the 5, minus 6048Q to the 6, and so on. Okay? So this is how it starts off. Now, this function delta of tau, this function of the different half plane, this had been studied, and so let's give this, we'll give these coefficients a name. The notation is tau of n, although if you read certain elementary number theory books, tau of n is sometimes used to denote the sum of divisors function. I'm sorry, the number of divisors function, but we should call that d of n. Tau would be this. In any case. So tau of n is just defined to be these coefficients, which are very mysterious numbers. Tau of 1 is 1, tau of 2 is minus 24. Does it count something? What's negative? Who knows? In any case, tau of n is just the notation for these mysterious integers, which seem to be both positive and negative. And this function delta of tau, though, had arisen in the 19th century in the study of elliptic curves. If you take, I'll make a remark here. If you take C modulo the lattice Z plus Z tau, so C mod a lattice is some kind of a torus, so it's an elliptic curve over Q, I'll just say, for each complex number in the upper half plane, this is some torus, it's an elliptic curve, it's an algebraic curve, and elliptic curves have invariance, numerical invariance, like there's a number called the discriminant, it has discriminant delta of tau. So this number, if you think of tau as a concrete number like I, you get a concrete elliptic curve, and it's cut out by something called the Weierstrass equation, and the discriminant of the cubic polynomial in the Weierstrass equation for this curve is that number. Okay? So this function has now, if you let tau vary, you get a function, and so this function had arisen before people like Jacobi and Klein had studied it in the 19th century, but it wasn't until the 20th century that somebody actually studied its power series expansion in e to the 2 pi I tau and looked closely at the numbers. In fact, it was exactly 100 years ago. Ramanujan in 1916, I don't know if it was this day, actually the paper was in 1916, maybe he did the work in 1950. But in any case, Ramanujan, well, he worked pretty fast. Maybe he did do it in 1916. So Ramanujan was the first person to look at these numbers and, oh, I guess the tau is not that tau. Anyway, so Ramanujan made several observations. Observed, or maybe I should say conjectured, on the basis, so he observed at least for n up to 30, he gave a table of values of tau of n for n going up to 30, and maybe he went farther, but the journal editor said, you know, just cut the table long enough. I found from experience from journal, they don't want lots and lots and lots, just enough to convey what you want. Anyway, so he conjectured a couple of properties. First conjecture, based on numerical evidence, was that the tau function is multiplicative, which in number theory doesn't mean that the value on the product is the product of the values, only when the inputs are relatively prime. Okay, that's what multiplicative functions in number theory. The value at mn, the value at n times value at n, when they're relatively prime. So this data allows us to check one example. Take n equals 2 and n equals 3. Example, 24 minus 24 times 252 had better be minus 6048. Okay? Tau of 6 is tau of 2 times tau of 3. Okay? I hope that's true. At least they're both negative, and they start with an 8, they end with an 8. So what this means then is the tau function is determined once you know it on prime powers. His next conjecture from observations was a recursive formula for its value on prime powers. Tau of, for prime numbers, for prime p and exponents r greater than or equal to 1, he observed there's a 3-term recursion. Tau of p to the r plus 1 is tau of p to the r, minus p to the 11th, tau of p to the r minus 1, obviously. So this was his 3-term connecting guys r plus 1, r, and r minus 1, granting knowledge of tau of p. So if you know tau of 2 is minus 24, then he's saying tau of 4, take r equals 1, p equals 2. Tau of 4 is tau of 2, tau of 2, tau of 2 squared minus 2 to the 11th, so it should be minus 24, 24 squared minus 2048 times 1. Okay, should be minus 1472. Okay, so it's a 3-term recursion, and the last conjecture he made was an estimate on how big tau of p as an integer up to sign could be. He said it could be no more than 2 for prime p, it's no more than 2 times p to the 11 halves, 2 times p to the 5.5. Okay, and he felt this was a sharp estimate. If you accept that and the other conjectures, you get an estimate on tau of n in general. It's at most d of n. Remember that function I said you shouldn't call tau of n? The number of divisors of n times n to the 5.5. So when n is a prime, primes have 2 divisors, one in themselves, positive divisor. And so it recovers this estimate, but this is a generalization for all n if you believe this and the other parts. Okay? So roughly it grows at worst like n to the 11 over 2, n to the 5.5. Actually, in Ramanujan's paper, this conjecture has a typographical error. He has the 2 over here. Is that the error? I think that's the, in any case, it's a typo. But he has this one there also, so clearly it was, yeah, he knew what he was talking about. So what can we do towards, so this conjecture sort of came out of nowhere. People had studied this function, and nobody had looked at its power series coefficients until Ramanujan. And it didn't actually take very long for the conjecture to be proved. Mordell, in the next year, 1917, I believe, proved Ramanujan's, there were 3 conjectures. The third one is way, way, way deeper than the first 2. Okay? So the first 2 were handled pretty quickly. Mordell gave a proof of the first 2, but it was sort of an ad hoc method. And several years later, Hecke found a systematic way to explain the first 2 conjectures by introducing a family of linear operators on spaces of modular forms. And so I want to show you how that works. So what happened was, the first 2 conjectures of Ramanujan were settled by Mordell and Hecke separately. And this leads to the theory of what are called Hecke operators. So I'll show you an example of Hecke operators and how they allow us to derive the conclusions of the first 2. The third one, though, is very deep. The third conjecture, this was settled, I should say this was settled quickly, did not take that long. This was settled in the 1970s by Deligne. And this was a consequence of his proof of the Bay conjectures for varieties over finite fields, where he got the Fields medal. And so the third conjecture is much, much deeper. I should say, Hecke showed, he made progress. He showed tau of p is at most 2 times p to the 6th. Ramanujan said 2 times p to the 5.5. Like, not quite, but pretty good. But to get from p to the 6th to p to the 5.5 requires an enormous amount of mathematics. All right? You have to connect this problem to algebraic geometry, find some varieties which you can interpret the tau of p's as traces of some operators or something, and to get the 5.5 was the Riemann hypothesis for varieties in a finite field. So very, very difficult to lessen the exponent. So I want to show you what some Hecke operators are, and so I will explain. So now let's define five. So Hecke's proof actually introduced a bunch of linear transformations called Hecke operators, Tn, from modular forms to modular forms of the same weight, satisfying a couple of properties. For example, they commute. The Hecke operator at Mn is the product of the Hecke operator at M times the Hecke operator at N if Mn are relatively prime. And the Hecke operator at p to the r plus 1 is the product of the Hecke operators indexed by p and p to the r minus p to the k minus 1, k being the weight, times the Hecke operator at p to the r minus 1 for prime p. And r at least 1. You can see that these operators satisfy recursive formulas, much like what Ramanujan was trying to prove for the coefficients of delta. And they also satisfy other properties, but I don't want to get into them. So I'm going to focus, if you believe such operators existed, this equation says the operator Tp determines the operator Tp squared, Tp cubed, and so on. And this one says if you know T prime powers, you know them all. So in theory, if you understand the Hecke operators indexed by primes, you can get all the rest. So I'm just going to tell you what the Pth Hecke operator is for primes. For prime P, let Tp mapping Mk to Mk by the following formula. Give me a modular form, F. TPF will be a new modular form. And TPF is this linear combination of functions, f of p tau, f of tau over p, tau plus 1 over p, tau plus 2 over p, and so on, up to tau plus p minus 1 over p. So it's this linear combination of coming from your original modular form f. So this is clear. This is a little finite sum. This is obviously holomorphic on the upper half plane. It's not obvious this is a modular form, but it's obviously holomorphic. It's obviously bounded as tau goes to infinity. But how does it behave as tau goes to tau plus 1? This is unchanged because p tau plus p. This is unchanged when tau goes to tau plus 1. And when tau goes to tau plus 1, these guys just get cyclically permuted around. Right? Because the original modular form of tau goes to tau plus 1 doesn't change. So if you have denominator of p and p minus 1 goes to p, it switches back. So this sum just gets cyclically permuted. So this thing certainly is invariant under tau goes to tau plus 1. And to study how the terms are permuted amongst each other, a little cyclic permutation in terms of the sum. For minus 1, for minus 1 over tau, what happens? So it turns out that, you're expecting to have the weight k transformation law. So it turns out if you plug in minus 1 over tau, this guy comes back to itself multiplied by tau to the k. False. If you replace tau by minus 1 over tau everywhere, this guy goes to the b equals 0 term times tau to the k. The b equals 0 term spits out as this guy times tau to the k. And the b equal 1 to p minus 1 terms get permuted amongst each other. The b term, when you plug in minus 1 over tau, turns into the minus 1 over b term mod p. They're all invertible mod p if b is not 0. Goes to the minus 1 over b terms. But in the end, the terms get permuted, each one multiplied by tau to the k, and so you still get the sum, you get that in the end. So this actually is a modular form, and in terms of Q expansions, if f is summing a n q to the n, TPF is summing a p n q to the n plus summing p to the k minus 1 a n q to the p n. So you on the q to the n, you still get a n gets replaced by a p n, but if the exponent is divisible by p, then you get some additional terms. So for example, the constant term is a0 plus p to the k minus 1 a0. So as I've said several times before, you can't look at something and say, oh yeah, that's obviously a modular form. No! The only reason that we know this is a modular form is because we had a different formula that we could check as a modular form, and then we just worked out what the Q expansion happened to be. It's totally not obvious that this expression is again a modular form, but it is. And to end, I want to show you how the fact that this is again a modular form lets you prove these first two conjectures of Ramanujan. Well, I'll just illustrate by a special case. Okay? Just so you can see the linearity, this linear operator is a useful thing. So the point is, M12 is a two-dimensional space, basis E12 and delta, and these are the modular forms that vanish at infinity. These ones certainly do not. Well, it's at 0. And so this modular form, since the constant term of this is p to the k minus 1 times the constant term of this plus 1 over p times, well, p to the k minus 1 times the constant term plus the constant term. Because f vanishes at infinity, so does TPF. So TP, each TP sends this subspace back to itself. This is a one-dimensional subspace. Delta is what's called an eigenform of all the TPs. So we get, it's one-dimensional space, so it has to be a scalar multiple for some complex number. Well, look at the coefficient of Q. Look at the coefficient of Q. What's the coefficient of Q in TPF? You never get a Q to the first, you just get AP. So the coefficient of Q on this side is the coefficient of Q to the P in the original thing. And on this side, because delta starts off as Q plus stuff, you just get lambda P. So the eigenvalue is actually, we can interpret the coefficient tau P as an eigenvalue of a linear operator. And so now, let's check. So I just want to do one example to convey the idea. Do you want to do like a case of the prime power or a case of this? Prime power. So let's show tau of p squared is tau of p minus p to the 11 times 1. Tau of p, right? When r is 1, you get 2, and r minus 1, yeah. So tau of 1 is 1. Okay? So let's check this. So all we have to do is let's look at the coefficient of, let's see, which one do I want to do? Let's look at the coefficient of q to the p. Okay? So the p here is a prime number. So where do you get a q to the p? So here if you have a q to the p, it's AP squared. So the coefficient on the left side, if you look at this equation, on the left side, the coefficient of q to the p, here you get an AP squared. So here our function is the delta function. So you get a tau of p squared. But you also get p to the 12 minus 1, p to the 11. So q to the p shows up here when n is 1. So you get p to the 11 times a1. So you get tau of p squared plus p to the 11. And that's equal to, on the other side, if you plug in delta, the coefficient of q to the p, and delta is tau of p, but we multiply by tau of p, you get tau of p, you get tau of p squared. Okay, so you can see that you get, now you just bring this over to the other side. And so if you look at the coefficients of different powers of q in the q expansion on both sides of this equation, if you look at the powers of p coefficients, then you can read off the recursion. And if you look at the powers of p times integers prime to p coefficients, you can read off that you can pull off powers of p out of integers. You can get the multiplicativity that way. And so the last thing that I want to say is that the reason that Ramanujan was looking at this is because he's interested in the analog of the zeta function. The L function of the delta modular form, if you take this Dirichlet series with these coefficients, all these recursions imply it has an Euler product decomposition. But unlike the Riemann zeta function, the factor at p is a reciprocal quadratic polynomial in 1 over p to the s, not a reciprocal linear polynomial in 1 over p to the s. And this would be true, for example, if the real part of s is greater than, say, for instance, I guess 6.5. Okay? This is convergence. And so it turns out that modular forms have L functions or zeta functions. You can take the coefficients of a modular form, like the delta function, and make them into the coefficients of the Dirichlet series. And the modularity condition of value at minus 1 over tau is tau to the k times the function makes you able to show that the Dirichlet series has an analytic continuation to the whole complex plane. This only converges in some right half plane. You get a continuation of the whole complex plane and a functional equation relating the values of s and k minus s, where k is the weight. So here you get a connection between the values at s and 12 minus s, and the middle is 6. And so we expect that this satisfies the Riemann hypothesis. All the zeros that are not obvious should lie on the line real part equals 6, like real part equals a half of the zeta function, and it really is, well, I can't say it's true, but numerically one can check such things. And for general modular forms, though, you don't have an Euler product. And in fact, there's a recent theorem, this is the last thing I'll say, of Andrew Booker and Frank Thorne, that says that for a modular form, for a modular form's L function, if it's not an eigenvector of all the Hecker operators, then its Dirichlet series, in fact, has zeros in the half plane where the Dirichlet series converges. So the place where the Riemann hypothesis takes place is outside the domain of convergence. And so, in some sense, we don't expect Euler products except for modular form L functions unless they're eigenforms, eigenvectors of all the Hecker operators. So if you ever hear number theory seem to be obsessed by Hecker eigenforms of all the Hecker operators, why they care so much about those? Because those are the only ones that could possibly satisfy a Riemann-type hypothesis for their L function. Okay? So these Hecker operators are really important. They single out the modular forms of most interest. Right? So I'll stop there. Thanks.